All right, so I'm going over. I don't see any other questions. Let's go ahead and move on to one of my favorite. That's one of these mixture problems. These ones, they tend to be a favorite problem because they, again, look very wordy. They look more complicated than they really are. But once you get down to them, they turn into some very nice equations and usually not too bad to solve. The tough part is really figuring out what's the moving pieces in here. How do you even set it up? So with these tank problems, we're again going to go through a process of just going things over, trying to figure out what the rate is. What is the derivative in here? And then move on from that and see how the rate is being affected. So in this particular problem, it looks like we're dealing with a tank and it's starting off with nice pure water. Pure water is flowing into it at 10 liters per minute. Now inside the tank, it's being mixed thoroughly, and you'll often see that with these problems. We need continual mixture in the tank itself. It looks like it's going to get mixed and it's going to flow out at a 10 liter per minute rate. Now, initially, the tank is going to contain 20 kilograms of salt dissolved in 500 liters of water. So we want to figure out how much salt will be in the tank after 30 minutes. All right, again, lots of information all kind of floating around in here, but we can make sense of it. There we are. So the first thing I want to think about is what is really changing in this problem. So I have water, I have salt, and what it's asking more about is like how much salt is going to be in the tank after 30 minutes. So in a way, it's like saying that, you know, the salt in the tank is going to change. It's starting off with a certain amount of salty solution, but then we're pumping in pure water, so that salt concentration is going to decrease. How is the salt concentration going to change? So I have, or I'm going to write that it's the rate of salt change. And of course, that's going to be my derivative, how that salt is changing. Now, how that salt really changes is a combination of two things. It's really going to come from new salt coming in, so the rate in, subtract the salt that's actually leaving the tank, so the rate out. If I can figure out those two things, then I'll have a much better handle on my overall salt rate of change. All right, so let's now start translating these things into more mathematical terms. Starting off with the rate of change of the salt. If I think of my y function as being my salt function, how much salt I'm really keeping track of, then this is going to be my dy dt, or I can say dy dx, you know, whatever I want to use for my units, but it's how the salt is changing over time. And now I want to get a good handle of how much salt is coming in and how much salt is leaving the tank. All right, initially it says that we will be pumping something into this tank, but what we're pumping into the tank is nice, pure water, so it doesn't have any salt coming in. So I can think of 0 kilograms of salt coming in at a rate of 10 liters per minute. So it may seem a little funny to write that in there, but essentially we just have 0. Now the rate out is going to be the interesting part of this one. So the rate out is going to depend on how much salt is actually in the tank. You know, after it gets in there, mixed around and maybe combined with what the water is already there, then it's going to start leaving the tank. So this is essentially a measure of, well, what's in the tank right now? What is its current concentration? So that'll be its current amount of salt, what I'm going to call as y. And we have 500 liters of water. So it's however many kilograms of salt we have in there divided by 500. And this is flowing out at a rate of, again, 10 liters per minute. So we are going to multiply that by 10. All right, so all that is looking pretty good. You'll notice that the only piece that I haven't used at this point is where it says initially the tank contains 20 kilograms of salt. That would be our initial condition. So if you want to put that somewhere else, that can say that at time 0, that this thing is actually just going to equal 20 kilograms of salt. All right, so we've set up our differential equation. We have our initial value. And now it really just comes to the solving process of this. You know, really saying, well, what kind of differential equation is it, and how do we get a solution out of here? Since we have some zeros and some tens in there, we have a little bit of simplifying. Let's do that before we actually get too far with the solving process. So dy dt, 0 times 10 is just going to be a 0. This 10 will reduce with the 500 in the bottom, so we have negative y all divided by 50. Excellent. So it looks like we have another separable differential equation, and in which case it's going to look an awful lot like solving the previous one. That is to say, if I want to get my terms all separated out here, we'll end up with a nice little 1 over y on the left, and then we'll end up taking the integral of a negative 1/50th dt. Then we can take the antiderivative, solve for those constants directly, see what we get out of there. Yeah, so what is this? This is the natural log of y. End up with the negative 1/50th t plus a mystery constant. We're going to use e on both sides of this. And we're going to combine our constant with that mystery e. So we'll have e to the negative 1/50th t. And then I can use the initial value to solve for my mystery c. So imagine plugging in 0 for your t. This should equal 20. That actually just gives us that c is equal to 20 right out front. All right, so this brand new equation is not a differential equation. It's just a standard old equation. But the important part about this one is it always gives us how much salt is in the tank at any given time. If I plug in 0, it's equal to 20. There's 20 kilograms when we start. If I plug in, let's see, what do we want? We want to know how much salt is going to be in there after 30 minutes. So if I plug in 30, it'll give me that new concentration. It'll give me the new kilograms of salt. All right, so let's plug in the 30 here. Let's see, where's my calculator? Ooh. So 20 times e to the negative 1 divided by 50 times 30. So it looks like after 30 minutes, I'm going to get almost 11 kilograms of salt left, but definitely a little bit less. And the fun part is, you can really use your intuition to get a handle if you're doing these problems correctly. So think about how this problem started off, okay? When it was first starting off this problem, there were 20 kilograms of salt in the tank. So let's say it was fairly salty. But we started putting in nice pure water into the tank. So the concentration, as you would expect, is going to go down. It's going to get reduced as we start putting in more pure water. It starts mixing around. It's going to continue getting less salty. And that's exactly what our equation is telling us. The fact that our rate here is a negative 1/50th, it has a decaying type of feature to it. It's going to get less salty over time. And if we check the actual amount after 30 minutes, then yeah, it's definitely less than 20. Some of that salt has been washed out of the tank. Good question. So I just found a few of the questions about this problem. Let's see if we can answer them. This one says, why is 0 times 10 for the rate in? Well, essentially, those are two different parts in there. Think of the 0 as being the amount of salt that's actually coming into the tank. So I'm going to write that as 0 kilograms of salt. 0 kilograms of salt. The 10 is actually just the flow rate. So 0 kilograms of salt are coming in at a rate of 10 liters per minute. Yeah. Could you explain how you got the rate out as salt divided by 500 times 10? Good question. So yeah, that's essentially the same two pieces that you're seeing, packaged in here. So the y here is giving me my kilograms of salt. But it's being dissolved in 500 liters of water. And then the 10 is really just the flow. So it's flowing out at 10 liters per minute.